Hello students, in today's lecture, we will be solving all numericals of optical fiber. So let us first quickly revise all the formulas, the important formulas which will help us in solving all the numericals are here. Numerical aperture is equal to refractive index of core, which is greater than that of cladding, under root 2 del, where del is the fractional change in refractive index, which is equal to refractive index of core minus refractive index of cladding upon refractive index of core. Numerical aperture is equal to 1 upon mu naught, where mu naught is refractive index of external medium, under root mu1 square minus mu2 square, where mu1 is refractive index of core and mu2 refractive index of cladding. If external medium is air, then mu naught is equal to 1 and numerical aperture formula becomes under root mu1 square minus mu2 square. V number is equal to pi into d, where d is diameter of the fiber, lambda naught is wavelength of monochromatic light propagating through the medium, into under root of numerical aperture. If external medium around the fiber has a refractive index of mu naught, then the formula gets multiplied by mu naught. Total number of modes which the fiber will support is equal to V square upon 2, provided V number is larger than unity. For single mode operation, the cutoff parameter V should be less than 2.4. Number of propagating modes is equal to 2a square pi square Na whole square upon lambda square. Number of modes in the graded index fiber is equal to 2a square pi square Na square upon lambda square into 2 into 1 upon 1 plus 2 by P, where P is profile index. Lot of numericals come on this formula of attenuation coefficient of fiber in decimals per kilometer, which is equal to 10 upon L. L is length of optical fiber, log base 10, output power upon input power, decibel per kilometer. And if we are indicating losses, we add the minus sign to this formula. First, we will begin with the very simple numericals where we are given refractive index of core and cladding, and you have to find the critical angle. So critical angle is sine inverse mu2 upon mu1. Simple, very simple. Critical angle at cladding and boundary, theta c is sine inverse mu naught upon mu2, and you get the answer. Simple numericals will all be consisting of refractive index of core, which will always be greater than refractive index of cladding. Here in this numerical, you have to find the numerical aperture and acceptance angle and how many reflections per meter are suffered. So at the steepest angle with respect to fiber axis. So there is a very simple trick involved here. See, first you find the numerical aperture, which is under root core refractive index square minus cladding. Use the simple formula a square minus b square is equal to a minus b into a plus b. Acceptance angle is equal to sine inverse into numerical aperture. Now this trick, at the steepest angle, the angle of incidence at the core cladding boundary will exceed the critical angle. And you have to actually find out the critical angle here in this question. You can see in the diagram also it has been explained to you that Fx is the axial distance traversed by the ray between two successive reflections suffered by the ray, and d is the core diameter. Then from this triangle, x is equal to d tan theta c, which is critical angle. So you get the distance x, number of reflections becomes equal to 1 upon x. If the fractional difference between core and cladding has been given and numerical aperture is given, you have to find the refractive index of core and cladding materials. So you have been given del Na formula is mu1 into under root 2 del. So mu1 is Na numerical aperture upon under root 2 del. You simply put the values and you get the answer. Determine the core radius necessary for single mode operation, where you have been given the refractive indices. What is the numerical aperture, critical angle, and maximum acceptance angle? This numerical can be very easy for B.Tech first year students. See, for single mode operation, cutoff V parameter should be less than 2.45 and 405. So you just check out what the V number is coming with this value, put the values, and you see A is coming out less than 4.089. And numerical aperture, taking the square root of this core cladding and using the formula A square minus B square. Maximum acceptance angle, alpha is sine inverse under root mu1 square minus mu2 square. Critical angle, sine inverse n2 upon n1, and you get the answer. Step index fiber has a core of this much diameter. Numerical aperture is this. You have to find the number of propagating modes at an operating wavelength of this. So number of propagating modes is 2a square pi square na square upon lambda square. Straight away put the values and you get your answer for number of modes. Step index fiber has core of refractive index 1.466, cladding 1.46. Find the maximum radius allowed for a fiber if it is supporting only one mode. See, fiber will support only one mode if its cutoff parameter is less than 2.4. That is 2.4. If the VA is, let us find it out. How much are we getting A after solving? 3.71 micrometer. So this is the allowed radius. See, this is micro. So you can say it is the allowed radius. Silica glass optical fiber has a core refractive index of 1.5, cladding 1.45. Simple numerical aperture. Just put the formula, put the values, and you get the answer. Numerical aperture and acceptance angle of an optical fiber. Na is under root mu1 square minus mu2 square. You get the answer. Acceptance angle alpha is sine inverse of Na. Optical fiber has the following characteristics. Fiber index, relative difference in the index. Find the value of numerical aperture and acceptance angle. Here you get your straight away answer. Calculate the fractional difference between core and cladding if refractive index has been given. So del is mu1 minus mu2 upon mu1. Calculate the numerical aperture, critical angle of a fiber for mu1 1.5 and mu2 1.45. Just you have to put the values and you get your answer. Velocity and wavelength of light of frequency while traveling through glass. We know the formula for velocity is c upon mu, and wavelength lambda is equal to v upon f. Just directly put the value and you get your answer. The core diameter of a multimode fiber is given, relative refractive index difference is given, operating at a wavelength is given. You have to find the refractive index of cladding, normalized frequency, total number of guided masses of the fiber. So you will very simply put the formula values. You get mu2, then you will find out mu2, and for here, after mu2, normalized frequency of cutoff, V number, you get the value here. Total number of guided mode in the step index fiber, N is equal to V square by 2. Next, this is, now these numericals are very common in exam. An optical fiber of length 150 meter has input power of 10 microwatt, output 9 microwatt. Find the loss. Losses, negative sign indicates losses, minus 10 log base 10 power of output upon power of input. Both the values are in microwatt, so don't change them. Straight away find out log and you get your answer. 1000 meter is 1 kilometer, change it into kilometer, loss for 1 kilometer. These questions are very common. They are asked optical fiber optical power after propagating through a fiber 500 meter long is reduced to 25%. Calculate the fiber loss. Loss minus 10 upon L log base 10 P naught upon Pi. You have been given the values of P naught and Pi. Put them, take log and get the answer. Next numerical. A signal of 100 microwatt injected into a fiber. The outcoming signal from the other end is so much. What is the attenuation loss? Minus 10 log base 10 P output upon P in. You get your answer. A communication system uses a 10-kilometer fiber having a loss this much. Compute the output power if input power is this much. So loss per kilometer in decibels is minus 10 upon L log base 10 P output upon P input. And then you take anti-log on both the sides and you get the answer. A 100-kilometer fiber is used in communication system. Fiber has a 3 decibel per kilometer loss. What will be the output power when input power fed at the input of fiber is 500 microwatt? Loss per kilometer is minus 10 upon L log base 10 P naught upon Pi. So you get total losses as minus 300 decibels. You take log on both the sides. P or naught is equal to Pi into 10 to the power of minus 30. So P naught is 5 into, this is a very small value, very small, 10 to the power of minus 28. But now these numericals for signal dispersion are for the higher university level course, but you can just have a look that time taken by ray in traversing an axial length of fiber is T equal to mu1L upon C cos theta, where C is light of velocity of light, mu1 refractive index. Time taken by rays making zero angle with fiber axis would be mu1L upon C. When theta is equal to theta C, the maximum case is going to occur. Time taken will be this much. Required time for amount of pulse broadening is maximum time minus minimum time. Pulse dispersion in graded index fiber is given by L upon 2C into mu1 minus mu2 whole square divided by mu2. Dispersion for multi-mode fiber, W2 minus W1, where W1 is width of pulse at input, W2 is width of pulse at output. Bandwidth length is 0.187 upon del T into spectral width of source. Material dispersion in optical fiber, lambda naught into wavelength in free space, C velocity of light. Total dispersion is equal to nodal, material and waveguide. And bandwidth distance is equal to 1 upon total dispersion. Single mode step index fiber is operating. You have been given the wavelength and material dispersion is given. Transmitted pulse is this much. Determine the maximum allowed bit rate for the fiber. So the total spreading due to dispersion, you put the values here. Single mode fiber, modal will be 0. So material and this waveguide, you get the received pulse width. Maximum allowed bit rate for fiber is 1 upon 2 into TR. Same process will be followed if multi-mode step index fiber has a dispersion of 10 nanoseconds per kilometer and it is to be operated at a bit rate of 100 megabits per seconds. Find the bandwidth. So